So let's get rolling. This is our last session. We're going to talk about how we now know that in finite element equations, the whole point of it is to be able to localize it into the behavior of a single element. We have a universal expression to be able to describe the behavior for fluid flow anyway, that says exactly what that conductance matrix would be. And so now, rather than being able to apply it to the one-dimensional element, which of course was identical to the one-dimensional element that we just derived by heuristics, now we can apply it to be able to solve for a two-dimensional problem. And so the simplest two-dimensional problem we can imagine is a triangular element, a so-called triangular constant gradient element. And the rationale for that, of course, is that it'll become clear soon enough. And so let's go through and do that. Let's figure out exactly what this conductance matrix looks like. We know that it should look something like Q equals KH. This is the form of it. We know that this conductance matrix is given by this generic form of an integral over a volume, this A transpose dA dV. This is volume, not velocity. And the individual components are that the A matrix, in this particular case, for a two-dimensional case, links what? It takes the derivative of heads with respect to x. It takes the derivative of heads with respect to y. And so the element that we'll deal with will be a triangular element that we'd like to define. We'll draw it again some other place later. It will have x and y coordinates. It will have nodes 1, 2, and 3. We've made the case that we always number them by convention counterclockwise, anticlockwise. And the A matrix that we want to develop is something that allows us to link the magnitudes of nodal heads, which would be heads at node 1, head at node 2, and head at node 3. We say we have two conditions at each node. One is a head, one is a flux. And this links the values of nodal heads to the gradients of those. And so these are our derivatives of the heads. These are the magnitudes of the nodal heads that we define here. And by definition, our A matrix is defined as that. The other way that we defined our A matrix was that the A matrix is equal to the derivatives with respect to x and the derivatives with respect to y of the shape function matrix. So these are just two different definitions. Same ultimate behavior. Same ultimate behavior. And so if we define, for instance, our shape function for the triangular element, we could differentiate that straight away and get the A matrix and therefore put this together. We know that the constitutive matrix is going to be, in two dimensions, is going to be conductivity in the x direction, 0, conductivity in the y direction for this 2x2 system. We'll talk about that later. And so really the deal is we might want to figure out exactly what, this is the only tough thing to figure out, is what is the magnitude of this matrix that links nodal values of heads with their gradients. And so that's our main job. Okay? So, that is, I suppose, is a recap and where we go from this. So the geometry is this. We've kind of alluded to that. We have three nodes. the nodes have coordinates, x and y, for nodes I, j, and m. I guess I labeled them m because k is used for hydraulic conductivity. So that's why it goes IJM, which is otherwise not very logical. We could have different values of conductivity in the x and the y directions if we wanted. And rather than define shape functions, you remember that when we derived the conductance matrix for this one-dimensional element, we didn't use shape functions, but we used the value of h. And so what was it? It was that h is equal to, head is equal to head at node 1, plus I think it was x over L times the difference in head 2 minus h1. If you look in your notes, I think it'll be that. So this is for the 1D case. So clearly in a two-dimensional case, then we have not just values of x, but also values of y. And so the appropriate head distribution is going to be this. And it's maybe instructive to think about it. If you draw this in a perspective, let's see if I have some space here. If we draw, say, this triangular element like this, as you imagine looking at it at an oblique view, horizontal element that you're looking at this way, you can imagine that the head at node 1 might be this value. The head at node 2 we might represent by a pin which is some height this, and the head at node 3 might be some pin here. Clearly these elevations, if you draw a plane that goes through them, it has the equation, this is just the equation of a plane, right? And we know that with 3 points we can definitely fit a plane through those 3 elevation points. And so that's the simplest shape function that we'll choose to use, which is really just an extension of the one that we used for this equation here. We had h2, we had h1, we joined them with a straight line. This is h equals mx plus c. Right? I guess c would be h1 if this is the coordinate system, and this is 0. So c would be h1, m would be h2 minus h1 over L. Is that right? I think. Yeah. So it's just, so in 1D, the line that goes through those 2 points is the equation of a straight line, which is exactly what this is. And this is just the same. This term here would be this. Right? This is m. And in 2 dimensions, the equation that goes through 3 points is the equation of a plane, and that, of course, is this. So that's what we'll use in this. We're guaranteed that it will go through those 3 points because a plane will always go between any 3 points by definition. So that's the plan. So let's see how we do that. We want to be able to figure out exactly what this conductance matrix is. I guess we've already alluded to the fact that it's going to be this. Let's make life easy for ourselves by making it so that it's aligned parallel and perpendicular to the x and y. So this would be the conductivity in the x direction. This would be the conductivity in the y direction, just as is kind of shown in this. Right? Some principal conductivity aligned in x, some principal conductivity aligned in y. If it was uniform conductivity, then I guess you could also represent the system by, if I can draw it out here, then the D matrix would also be equal to hydraulic conductivity times 1, 0, 0, 1. That's just another way of writing this if it was homogeneous. This is anisotropic. These terms would exist if instead of being aligned with the principal conductivities in the x and y direction, if they're aligned, inclined relative to x and y. You'd end up with these off-diagonal terms, but we won't worry about that here. And of course this goes into define Darcy's law. It says that the velocity of flow in the x direction is equal to the head gradient in x times this term plus the head gradient in y times this term. If it's 0, then it's just our normal Darcy's law, which we're familiar with. So the D matrix or constitutive matrix is pretty straightforward to be able to define. And the A matrix is just something that links nodal values of heads. So this will be H1, H2, H3 with the gradients of heads. And of course we have gradients in two directions. This is just my shorthand for this. Right? This term here is this term here is this, and we have to figure out what this matrix is, right? Because we want to be able to use it twice up here. So that's our task. So what do we do? Well, what we could do is these are the expressions we want. And so if, for instance, we can figure out exactly what this is, and we equate it to this, then we should be able to figure out exactly what this A matrix is. So if we can figure out both what these derivatives are, then we should be able to figure out what the A matrix is. So we take this expression, we differentiate with respect to x. If you differentiate with respect to x, you lose the constant, you lose this term here, and you're left with the derivative of this, which is just equal to b. Right? The derivative of x is equal to 1, and so this is this. I'm going to get rid of that because I don't want to mark it up. If we want to get this second term now, the derivative of head with respect to y, we differentiate this with respect to y. So this we lose, this we lose, derivative of this with respect to y, this becomes 1, this becomes c, it's this. So these are the terms. So we know that the values of each of these two components should be b and c. Remember that this A is the A matrix. Remember that it's confusing that this, I've used this term here. This is the constant, which is just a constant in the equation of a plane. It's not the same as this. And so what we need to do is we'd like to be able to figure out exactly what the magnitudes of B and C are. Because if we know what B and C are, we know that they're the same as these gradients. If we know they're the same as these gradients, then we basically are, and if we can define these gradients in terms of the nodal values at the head, at the nodes, the head values at the nodes, then we know this, and the only thing that we don't know is the value of A, which we'd like to figure out. So that's where we're going. So one way in which we can figure out what the values of B and C are to be able to write this equation. So let me go back and get rid of those lines that we have there, just because I can. And so what we could do is we like to figure out what the values of B and C are that go into this. So the easiest way to do that is to go back to this idea and say, if we knew what these heads were at these points, then what we could do is we could write the equation for the plane at this particular point here, and we know what the head is, and so we should be able to, if we do it 3 times, so we write the equation for the plane here in terms of h1, we write the equation for the plane here in terms of h2, and we write the equation for the plane here in terms of h3, we end up with 3 equations. We have terms a, b, and c in those equations, and so we should be able to solve for a, b, and c as a function of h1, h2, and h3. So that's really our role. And so that's exactly what we're attempting to do here. We write the equation in terms of the head at node I, node 1. It's a value of a we don't know. We certainly know the coordinate of node I. We certainly know the y coordinate of node I, but we don't know c. So we can write it at node 1, or node I. We can write it at node 2, or j, I guess. And we can also write it at node 3, which is n. We know what these heads are at each of those nodes, or we would do, right, by definition. We know what the coordinates are for each of those nodes, but we don't know what A, B, or C are. We can rewrite this equation, or three equations, as a matrix, which is this form here. We think we'll know these. We'd like to know these, and we certainly know everything in this box here, right? We know the coordinates of all the nodes in our system. And so what we could do is we could invert this, we could rearrange it. And I don't know if I included it in here. If you want to refresh your memory of how to invert an equation that's written in terms of these, the standard result is that the inverse of this equation that links this to this is basically this. Is it the determinant? So what is it? It's equal to 1 times this minus this times this, right? 1 times this minus this times this. The term, this next one is, if I go back, you'll remember this from your, maybe you'll remember it more recently than this. The term that goes here is equal to this term. Is that right? Why am I thinking that? It's not the determinant of this. I guess it's switched, isn't it? So yeah, it's the determinant of those components. I guess I'm not doing a very good job on that right now. So these individual terms are just the from solving this. So it definitely is this times this times this times this times this. The term that goes here must be xm and yl. This actually this term, isn't it? It's this times 1 times this times this. Ym minus xi, which is this, and then this minus this, which is this other term here, and so on. Anyway, it doesn't matter. The bottom line is that there's a standard result that allows you to take the matrix which is defined in terms that we know, which is this A matrix, uppercase A matrix here, and instead of defining unknown values of this and known values, we can switch it with the inverse of this, and the inverse is just this standard result. And 1 over 2 times the determinant is equal to, that is equal to this times these two, which is this, and then the other term minus this times this and this, which is these two terms, which exist here. And so that's basically a standard result. So the only important thing, I guess, to know is that you can definitely define what A, B, and C are as a function of heads just by this, which is fully defined. All these are numbers we know because we know the x-coordinates of all the elements within the system. And so if we go back and apply that, without making this too long, is that this is the result that we initially have, where we think that we know what these values are. We don't know what these values are. We can rearrange it so that we can define these values as a function of heads and as a function of a manipulated matrix from here, which is recast in terms of these, where these individual values are just these numbers that go here, right, by definition. This is 1 over the determinant. This term here is, in case it's not clear, is just 1 over 2 times delta. This is the determinant of this component. The reason it's written like this, 2 times a triangle, is that this is the determinant is 2 times the area of the triangle. And so the reason that the nodes are numbered counterclockwise is that when you calculate the determinant from nodes that are numbered counterclockwise, it gives you a positive value for the area. If you number them clockwise, then the value of the area that you get is negative, and you just have to put a minus sign. So the reason for the convention is just so you get a positive area out of the system. And so now we know immediately what these terms are. They're just numbers that we can calculate from the nodes. This is 2 times the area of the triangle element. And then so what we can do is, we want to know, if you recall, we want to know what B is because the change in head with X is the equivalent of B, and the change in head with Y is the equivalent of C. Remember that from a bit earlier, right? These components here. That was our standard result just by differentiating this. And so if we know what these values are, then we immediately are able to calculate our A matrix. And so this is equal to dH dx. This is equal to dH dy. And so in other words, what we could do is we could just take this matrix relationship. We can throw away this top line. We don't need it anymore. And we're left with nodes 1, 2, and 3 multiplied by these two gives us the value of these components here. And that's exactly what's written here. And so by definition, the gradients of heads in X and Y are linked to the nodal values of heads by some matrix. This is the relationship that results. And so by definition, this component here with these geometric terms is purely this A matrix. And so we have that. And so that's what we need. So the only thing that we needed when we started off on this journey was we needed to be able to figure out what the constitutive matrix was, which we know, we've defined here, and what the value of A is, we've also defined this. I suppose we could also write this expression as the integral times thickness. We know that dV is equal to a thickness times dx dy. Right? So if you think of a triangular element that looks like this, like a wedge of cheese, it certainly has a thickness attached to it. S. And so this is just this transformation. And so in other words, if we write thickness times the integral A transpose dA dx dy, this is over the area, and that's just the transformation of this. And so now if we have the value of this A matrix, then we're in a place that we can actually do something to be able to calculate the behavior of the system, the conductance matrix. So if we zoom down to this is exactly what we're going to attempt to do. We know now what this A matrix is and what A transpose is. It's just this term here. It's purely a function of the nodal coordinates, so it's absolutely defined. It's not a function of anything else. And so we have that. And I guess we can note a couple of other things. This is the matrix we have. I kind of simplified it in terms of area, but we perhaps didn't need to do that. What do we know about this? The A matrix, each of these terms is a constant. It doesn't vary in space. It's a function of nodal values, and so since each one of these is a constant, we can take all the components of this are a constant. All the components of this in one element are a constant as well. A transpose is just the same components as A, so all of these are constant. So if they're constant, then we can take them outside the integration sign. If we take them outside the integration sign, then we can think about what this integral means. The integral of 1 over a volume, which is really what this is, right? This is just 1 times an integral over a volume. By definition, this is just what we've called before the area of the triangle. This is, sorry, not the area, it's the volume, isn't it? So it's the area times thickness. This is area equals volume. And so that's exactly what we have below. So it's actually a very easy matrix to calculate because we know that by definition, since the heads are defined by the plane, by definition, if you take an integration of a plane in any direction, it ends up being a constant, right? Because if you look at a trace in the x direction on a plane, it's just a line with an inclination. A line has constant inclination, it doesn't bend as you go up or down, so by definition, take the derivative of that inclined line, it's just a constant, either in x and y. And so that's worthwhile knowing. So we get rid of the problem of being able to having to do any integration. And this is actually the derivation of how to integrate, how to take the inverse of a matrix. So the bottom line is that we're able to calculate exactly what the terms of A are. And the terms of A are A2, 1, etc. We have 6 terms which we can calculate. And so now we need to do something with it. And so what do we do in terms of how we put together the conductance matrix? So we know that now we've localized everything into a single matrix, which allows us to be able to define for this template for a triangular element what the conductance matrix is. So if we think of a mesh that now comprises 3 elements, element 1, element 2, and element 3, we have this same dilemma as we had before. How do we put together the global conductance matrix? So what we can do is we can look at this, and this is our mesh, which comprises 1, 2, 3, 4, 5 elements, nodes rather. Each of these nodes are part of a system which involves elements 1, 2, and 3. And individually, we can also define within the elements a local element node number, which is node number 2, 1, 2, and 3, which in this case is the same as the global ones. But for this element, local node 1 is equal to global node 2, local node 2 is equal to global node 4, and local node 3 is equal to 3. So we just need to realize that when we number our nodes, we number them counterclockwise, and it doesn't matter which order we could do it. We could equally make this 1, 2, and 3. It absolutely doesn't matter. And so the idea is that now, when we localize this, we can calculate what the conductance matrix is for element number 1, this one here. And so we could calculate exactly what the terms would be in this matrix. What do we know in terms of what it looks like? If we draw out this matrix, we have, what is this? This is 2 rows and 3 columns. This is 2 rows and 2 columns. And this is 3 rows and 2 columns. And so when we multiply this out, we multiply these two together with each other, and we get something that is, again, 2 by 3. This is rows, if you like, and columns. And if you multiply, let's just draw it, I guess, what would it be? 2 rows, and so in other words, it would look like this. And we're multiplying it by something that looks like this. So what we end up with is we multiply this by this, and this by this, and we get this ultimately results in something that will be 3 by 3. So I know you all know that, but the point is that we end up with a 3 by 3 matrix out of this. So this is A transpose dA, this is dA, and this is A transpose. So we're just calculating this. So we end up with a 3 by 3 matrix as a result of this. And so we can calculate what that 3 by 3 matrix is. It's going to be this, right? This is going to be the conductance matrix for element number 1. And if you look at this, what am I doing? This is local node 1, local node 2, local node 3. Local node 1, local node 2, local node 3. And in this particular case, local node 1 is equal to global node 1. local node 2 is equal to global node 2, and local node 3 is equal to 3. And so these are both local and global node numbers, and they conform to this. But when we look at 2, now the system's changed. So I guess I've written it on here already. This is, again, local node 1, local node 2, and local node 3. And this is local node 1, local node 2, and local node 3 in terms of our conductance matrix. But this local node 1 is equal to this global node 2. So this is this. This local node 2 is equal to global node 4, which is this. And 3 is actually equal to 3. And so these numbers are just the numbers of the global system. And there's a reason for us to do this. Perhaps I should label them. So this is local. This is global. And you can do the same for the top one as well. Same deal. So element number 3, local node 1, which would be the first column, would be equal to 4, right? Local node 2 would be equal to 5. And local node 3 is equal to 3. And actually you can see this numbering in these subscripts that are used there. And so the method to the madness, and also you see that this global numbering is also 2, 4, 3, 2, 4, 3. And so the reason for doing that is it's actually absolutely straightforward to compose the stiffness matrices, or the conductance matrices, just by using this indexing that makes you put the right values in the right place. So we have these 3 individual template matrices for the 3 individual elements, and we want to make a global system of equations, and the global system, well, I guess it's written down here, is that Q equals KH. And so the question is, what are the size of these matrices going to be? H is going to be in terms of rows and columns. So rows will be 5. This will be 5 rows and 1 column. And this will be 5 by 5. Has to be right. We have 5 nodes, 1, 2, 3, 4, 5. There'll be 5 values of heads, H1, H2, H3, H4, and H5. And those will be linked in some way to 5 values of fluxes, H1 through 5. And the shape of the matrix that has to link those has to be a 5 by 5 matrix to be able to do that. And so our job now, we've got the conductance matrices at the individual element level. We just have to make sure they go in the right places. You remember we did it before by just filling blocks up at a time. It might not be quite so simple this time, so let's see how we do it. Okay. First one's easy, right? So local 1 is global 1. So this is global 1, global 2, global 3. So it's actually, it just occupies the first 3 locations. So the first 3 locations are conductance for node 1. The terms just translate in directly into this location on these first ones that I'm doing. So that's the easy one, because this links values of nodes 1, 2, and 3. 1, 2, and 3 are also the local numbers with 1, 2, and 3. So you'd expect that it fills up this first 3 by 3 quadrant, I guess it is. So those are the easy ones. Is there a pattern here? In terms of the indices that we've added, 1, 1 is in 1, 1. 1, 2 is in 1, 2. 1, 3 is in 1, 3. So it's really just following the indexing. So what we're basically doing is, if we label these in terms of the global node numbers, then we're guaranteed to put it in the right place. This is 2, 2. This is row 2, column 4. Row 2, column 3 in terms of the global numbers. And so all we need to do is we need to make sure that now that we take this one, where is it going to go? I don't know if I get both on the same page or if it's too small. Maybe I can get them both on the, yeah, I can get them both on the same page. So 2, 2 is going to go exactly here. 2, 4 will be on the same row, and it will be here. And 2, 3 will be on the same row, and it will go right here. So Roman 2 means element number 2, and these are the node numbers. And so we can add the other ones the same way. If we want to take, for instance, where does this one go? We have to do it for all of them. This goes on row 3, column 4. Row 3, column 4 would be this one. 3, 4. 3, 4. And so it just ends up being put into the right location. This might be too low, right, because your screens. But that's the mechanism. And so if you do that, you can try it also for the one-dimensional case. It'll show you it's exactly the way to do it. And that's the way that all finite element codes assemble the global conductance matrix. They index the elements of the conductance matrix relative to the global node numbers, and then it puts it in the right place in the global matrix from the template element matrix, local matrix, just by using that indexing. The other reason for doing this with flow first as well, we mentioned that for flow we only have a scalar value, so there's 1 degree of freedom per node. If you have displacements, then you have a displacement in x and a displacement in y. And so when you develop the finite element matrices for solid mechanics problems in 2 dimensions, for a 3-noded element, you'd have 6 degrees of freedom. Displacements in the x and y at node 1, displacements in x and y at node 2, and at node 3. And so then, instead of indexing it relative to the nodes, which we've done here, because one node has 1 degree of freedom, we index it relative to the degrees of freedom. And we'll talk about that in due course. We don't need to talk about it now. And so basically we now have the conductance matrix all put together in the right place, and we can do that. So what I propose to do is I'll do a very quick example of the magnitudes of the conductance matrix, and then we'll use this little EG-FEM code to be able to look at how that gets done on a small problem. I think I have it set up in some way. Okay. So here's let's do two examples. So this is the idea. This will cement the ideas. And so you can think of we're going to solve a problem for geometry that looks like this. The geometry happens to look like a rectangle. And we're going to divide that rectangle into 2 elements. And again, the idea of the finite element method is that you can localize behavior in a single element, and if you can calculate the conductance matrix for one element, then you can put it together for the whole system. So we'll do it for one element at a time. This is what the element looks like. The geometry of this is 1 in height, and this is 2 in length. So likewise, that's the shape of this. The hydraulic conductivity is equal to 1 meter per second. The thickness into the page is 1. And so we can put together all the components we need for this. This is our geometry, 0, 0, 2, 0, and 0, 1. We need to put together the A matrix, which defines this behavior. Do we know what that A matrix looks like? I think we do, from what we talked about before. It's going to be this, right? So this is the A matrix is going to be this part here, right? So remember that we need just this portion below here. This is dH dx. This is dH dy. And let's actually draw. I'm going to just zip back and look at the geometry again, and I'm going to draw it on this same figure. So okay. Tell me if I get it wrong. Draw it here. So it looks like this. This is was it that? Was it IJM in that order? Yes. So this is J, and this is M. This is 0, 0. X equals 0. So this is XY of node I. This is 2, 0. And this is 0, 1. And so this is the relationship that we want to be able to define right here. And I know I have the advantage in this, in that I get to scribble things out. You perhaps can't. But what will these values be? So yj minus ym. So yj is 0 minus ym, which is 1. So I think this is minus 1. Ym minus yi. So ym is 1 minus 0 is 1. And yi minus yj is 0 minus 0, which is 0. Likewise for this, xm minus xj, xm is 0 minus 2, so this is minus 2, I think. xi minus xm, this is 0 minus 0, so I guess that's 0. Hopefully this is right. Xj minus xi is 2 minus 0, which is 2. So we have this matrix. We know that, well, let me just check to see, so that's 1 minus 1. Let's see if they're in the right order, just to see if we've done it maybe correctly. Yeah, I think we have, okay. And we have to divide through by 2 times one over the determinant. This is the determinant. It's also equal to 2 times the area. So the area of this triangle is length 2 times 1. So the area is equal to 2 over 2, which is 1. So the area of the triangle is equal to 1. So 1 over 2 times the area is equal to a half. And so this term here is equal to a half. And so the matrix that we get out of this for the A matrix should be equal to a half multiplied by minus 1, 1, 0, minus 2, I'm just taking these numbers here, 0 and 2, hopefully it's right, and I guess multiplied by the thickness as well, which you can take as 1. So hopefully this expression here is equal to what we have on the next sheet. Yeah. I left it at this, so it knows. So this is right, so this is right, this is right, this is right, and this is right. And this term here is just equal to a half. And so that's the A matrix for this. And so now we know that we can calculate the conductance matrix just by taking the A matrix, the conductance matrix, and the transpose of the A matrix. And if we just do those multiplications, so multiplying this by this, when you multiply these two together, what do you get out of it? This is the identity matrix. So you get 1 over 2 times the area multiplied by just -1, 1, 0, -2, 0, 2, right? So in other words, you multiply 1 by this and 0 by this and add the two together, you get the top line. Then you do it along the bottom line and you get 0 times this plus 1 times this, which is this term here. So you end up with this. And when you multiply these together, well, you get -1 times -1, which is 1, times -2 times -2, which is 4. So this term should be 5. Indeed it is. So this is it. And so this term here, I guess, is 1 over 4. Just because of, we know what this is, this here. So that's it. So we have the ability to be able to get the conductance matrix. We need it also, if we want to solve a problem, we need it for the other shape. So in other words, what we've done right now is get this one here, which we have. But we need to also get this. Actually, you can do it by transposition, by transposing it. I'm not sure I can do it here now, but I think you can do it by that. You definitely can do it by that. So what do we notice about this? I haven't mentioned this before. We talked about the one-dimensional elements that we had. But the other thing that's interesting about these elements and that makes finite elements quite a stable method is that always the matrices are quite well behaved. They're always positive definite and symmetric. Symmetric. So positive definite means that the numbers on the leading diagonal are always positive. They're always definite, which means they're not zeros, because that's kind of a problem when you solve matrix equations if you have zeros on the leading diagonal. So being positive definite is very nice. They're often strongly banded on the leading diagonal because, well, they just work out that way. And they're symmetric. So you see that the term above here is the same as this. You see that -4 and -4 is this. And you see that 0, and this is this. And so the interesting thing about that is that because they're symmetric, when you solve the equations, well, when you assemble the equations, you only have to figure out what the top triangle is, because you know that if you know all the components in this top bound are, by definition you know all of the lower ones as well. So you only have to calculate the top ones. And then when you solve the system of equations, you can use a symmetric solver, which is much faster and many fewer calculations than if you solve a non-symmetric matrix. And it works out better as well. So that's one thing that's related to this. The other thing which is interesting to note is, well, do you notice, well, let me ask you. Let's see if I can get you to talk. Do you notice anything about that matrix? Anything else about the matrix? That is unusual. That's probably a bizarre, kind of a random question. So if you add up all the terms on any line, they all add to 0. Any line or any column, they all add to 0. And that's always the case. And you can physically rationalize why that would be the case. Well, I guess I should ask you the question. Can you rationalize why that would be the case? And you can, of course. And the rationale is this. I'm going to try and draw. I want to make it small enough so I can get that on the same page. So remember this, 5 minus 1 minus 4. Memorize that matrix, because I'm going to try and redraw it. So here we go. 5 minus. I guess I don't need too much of it, right? Because I should be able to minus 1, 1, 0. I guess I should know that, right? Minus 1, 1, 0. And do I have enough to be able to put the rest together? Well, I definitely know that this has to be a 4, right? I definitely know that this has to be a 0, but I guess I don't know the value on the leading diagonal. It's 4. Yes, I do. I do know what it is, because it has to add up to 0. And so the rationale is this. If you take this element, and say you put the value of head 1 equals 1, say you put the value of head 2 equals 1, and say you put the value of H3 equals 1, this gives you the flow rate out of Q1, Q2, Q3. And this gives you H1, H2, H3. We've said that these are equal to 1. So why would it be that these numbers all have to add up to 0? Well, think about the physical system. So you have heads of these are equal to 1. What's the magnitude of the gradient in the element? Right? Has to be. Head at node 1, head at node 2, head at node 3, dead flat. Gradient has to be 0. And so what does Darcy's law tell us? It tells us that the flow rate or the velocity is equal to minus k dh dx. If this is 0 and this is finite, then by definition this has to be 0. If this is 0, when these are equal to 1, 5 times 1 minus 1 times 1 plus 4 times 1, by definition these have to equal 0. So it makes perfect sense. The fact that continuity, volume in equals volume, or the fact that there's 0 flow in this system means that basically these have to sum to, every single row has to sum to 0 if you multiply it by a head which is equal to 1. So I think that's kind of interesting. Head could be 2 uniformly, it doesn't matter, you still get the same result, right? So that's the reason for that. And so the final parting shot, I suppose, is now that we'd like to be able to use this in a useful way to be able to define our system. So what we have is we've calculated what the conductance matrix is for node number 1. This is geometry, bless you. And so we have this, and it's this, right? If we do the nodal numbering, this was 1, 2, 3 locally, and this was global 1, 2, 4. So that's what this is. 1, 2, 4. 1, 2, 4. If we do the same thing for the other element, then this is local, what must be this? This is 2. So this must be local 1. This must be local 2. And this must be local 3, just from this numbering. 2, 3, 4. 2, 3, 2, 3, 4. And so this is the numbering for this. And then we want to be able to solve this problem where we have 4 values of heads, 4 values of fluxes, and so the global matrix has to have 4 components, 1, 2, 3, 4, 1, 2, 3, 4. And so if we take this one, 1, 1 goes here, 2, 1 goes here, 4, 1 goes here, etc. Again, these just repeat. So these are the ones that go here. And these ones as well. Need different colors, don't I, for this, really? So it's this, this, and this. So you see the pattern occupying this. Yeah, see the pattern. The missing gap is on this line here. And if we look at this, this is 2, 2. So this is this one. This is 2, 3, which is this one. And 2, 4 just turns out to be a 0. And so we end up with the matrix. And so, again, if we now try and solve the system, so we didn't really say what the boundary conditions are for this. Let's take this block. We make the head here equal to 0. We make the head here equal to 1. Clearly that's going to cause a flow in this direction from high to low. 1 meter into the page. We have the conductance matrix for this, and we know this would be H2 is equal to 1. H3 is equal to 1, H2 is equal to 1, H4 is equal to 0, and H1 is equal to 0. And so now if we put that together with this is defined 0, this is downstream end, this is the upstream end, and we actually don't have to solve anything. We can just multiply these defined conditions through by these known values from the conductance matrices, and we end up with the flow rates being equal to this. And so coming out of the bottom, going into the top at nodes 2 and 3, we have 2 over 4, which is these two together. Coming out of the top part, we have minus 2 over 4. And the question is, what does Darcy's law tell us what it should be? If we write Darcy's law for this, we have Q is equal to A K dH dx. So the area of this face is equal to 1 times 1. Conductivity is 1. And the gradient has to be, it changes by 1 over a length of 2, which is equal to a half. Be meters cubed per second. And indeed, that's exactly what we get. Discharge out of one side is minus a half, discharge in is plus a half, depending on our sign convention. And I guess that same calculation is done right down there. So that's it. And so that's the mechanism. And so that is the mechanism that is used in all finite element codes, COMSOL, legacy codes from the 1970s, 60s, 70s, 80s, which COMSOL has really just evolved from. It's the mechanism that's used. You localize the conductance matrix. We have a general expression, this integral A transpose dA expression that defines what the conductance matrix is. We can define it for any particular element. We chose a triangular element that has a particular shape function on it, and then we can then put that in the right locations. What else? Well, let's try. See if I can do this quickly. This routine also may allow us to do the same thing. Perhaps it's useful to be able to look at this. The rationale is that, so you have this, the library of elements. So 2, 1 must be a triangular element that looks, I don't know how big or small that is for you on the screen. But this is a triangular element, uses the same kinds of ideas. The information that you give it is, that get passed to it in the code, are what the hydraulic conductivity is, what the element thickness is, what the other properties might be if you have them. It needs the x and y coordinates, x1 and x2 of node 1, the x and y coordinates of node 2, and the x and y coordinates of node 3. And if you look at this, what does it do? It calculates the value of the conductivity matrix. This is conductivity multiplied by 1, 0, 0, 1, as we had before. This is the D matrix. It calculates the value of the determinant, which I think is B. No, I bet you D2 is the determinant. It calculates the components. Yeah, okay, so this is it. This is 1 over 2 times the area of the triangle. This is the rest of the A matrix. Term A11, sorry, A21 rather, A22, and A23. It's just using the coordinates to do that. It's A31, called B31 here. It's A32, and it's A33 on the bottom. So in other words, it's this, this matrix here. If I can draw around it, it's just calculating that. And then it takes them both and it multiplies them together. So A transpose, which is, this is MATLAB code for A transpose. D is the conductance matrix, and A original times the area of the element and times the thickness. This is just the volume, right? These last two terms. So remember, we have to calculate this term here. So we have to calculate A transpose. So I guess in MATLAB terminology, this is A prime. This is D times A, which is this part here, and it's times thickness times area, I think I called it. And that's what it is. And so that's basically what's put into a stiffness subroutine, and it kicks out back to the rest of the program this KL. K means conductance matrix, stiffness matrix. L means local, and it gets sent back to the main routine. And so if we wanted to execute this, which we could do, I think we should do. Okay, let's do this. We have to, right. So bear with me. So what do we need to do? We can get rid of this. No, don't save changes. Don't get rid of this. I want to add the two components, which are the input file, which I think is this one, and I want to add the element subroutine, so it will execute. I think it's this one. So this is the element subroutine we just looked at. This is the data file, and you might recognize this. This is the actual example, right? These are the nodal coordinates. Node number 1 is x equals 1 and y equals 1. And so this is it. Node number 1 is x equals 1, y equals 1. I think this is node 1. I think this is node 2, so this would be x equals 3, y equals 1. That is. Oops. X equals 3, y equals 1, yes. So node 2 is x equals 3, y equals 1. Node 3 would be x equals 3, y equals 2 above it. And this one would be node 4, which is directly above 1, 1, which is 1, 2. So this column are the x coordinates. This column are the y coordinates of nodes 1, 2, 3, and 4. This is the magnitudes. This is the way to define the elements. This is the type of element, 2, 1, two-dimensional, and 1 is for flow. This is the hydraulic conductivity of 1. This is the thickness of 1. And this is the capacitance, which we don't use. So these are just defined locally within the element. And these are the addresses of the local element, the nodal numbers in the element. So this is element number 1. It has material number 1, and local node 1 is equal to global node 1. Local node 2 is equal to global node 2, and local node 3 is equal to global node 4. So is that right? local 1 is global 1, local 2 is global 2, and local 3 is global 4. So that's exactly right. And likewise for the other element. Element number 2, local node 1 is global 2, local node 2 is global 3, and local node, actually you can do it, you can see it beside it, right? Local node 1 is global 2. Local node 1 is global 2, local node 2 is global 3, and local node 3 is global 4. So that's what these are. And then the boundary conditions for nodes, all of the nodes are head boundary conditions, which is this code here. And the magnitudes of those heads are that 1 and 4 are 0 heads, and 3 and 2 are heads of, of 1. And that's all we need to run it. And so let me see if I can set it up. I just have to do a couple of things. I think I need to change this to 1. Whoops. I think that's all I need to do. Let's see if it runs. Let me go back to here. Let me I want to change something. I want to get rid of everything. Is this to clear it? One of these is clearing the history. Oh, I thought it was this. I don't want to do something that completely screws it up. Clear console. Right, that's what it does. So now if we run it, it's got a clear console, but let's try it. So we run it. You can see at the bottom. Without belaboring the point, it comes out with these, well, it's probably useful to look at the top. So what do? We have a local conductance matrix, which is 3 by 3. Don't care about the damping. We put that into the global one, which goes into these locations, which must look like we did before in this, right? So this is located, this is occupied, and this is occupied. But this one is skipped, and this one is skipped. So that's exactly what you see in this case. This is skipped, and this is skipped across here. So that's the global stiffness with the element number 1 in it. If we do the second element, we end up with another stiffness matrix, conductance matrix. Once we add that into it, it looks like the one should be the same one we have here. You can see just under here, this is 4 plus 1 divided by 4. So that should be 5 over 4, which is 1.25. This is minus 1, which is minus 1. Just worked out that way. And then when you do the solution, you end up with applying a head of 0 at nodes 1 and 4, heads 1 at nodes 2 and 3. They give you, trying to think what that is, initial calculations, but these are the fluxes that come out of it. Plus a quarter, minus a quarter, minus a quarter, plus a quarter. And those are exactly what this comes out to be. And so it's not a very sophisticated code, but it actually does all the things that a regular finite element code does. And so it's useful and maybe instructive in that. And so if you wish to play with it, you can certainly do that. And so actually we've done a fair bit. I think so today we've actually gone from 0 to something quite significant. We've looked at flow problems. We've shown that for flow problems in very simple one-dimensional elements, we can trick ourselves into believing that we can calculate based on logic what the conductance matrix would be for a single two-noded element. We've shown how we can put those together to solve a problem that includes more than one element to be able to solve a system in the steady state. We've developed the equations that describe flow in multi-dimensions, both 2 and 3 dimensions, and both transient behavior as well. And we've made a first stab at being able to define the magnitudes of the conductance matrices that are relevant for triangular elements, the simplest element in 2D, and we've implemented it to be able to actually solve a relatively simple problem, but at each stage of the way, we've talked about whether we're actually rationally solving these problems or not, whether we're right or whether we're wrong, and I think we're right because we've checked it at every stage of our way through there. So that's what we've talked about so far. I guess there is no assignment tonight because we carried everything out here. When we talk next time, what we will do is, may seem a bit esoteric, but what we can do is, in addition to these simple elements that we've talked about today, with two nodes at the end and a uniform gradient and a linearly varying head distribution across them, we can also develop much more sophisticated elements, the kinds of elements that, for instance, COMSOL uses, which have more complicated functions, and the way to do that is to develop what are called isoparametric elements. So we'll start with that next time.